this video about black holes. Here we're considering the evolution of really massive stars, which after they've gone through their life cycle, gone through a huge supernova, it will leave a neutron core greater than 2.5 times the mass of our own sun. So you already recognise a black hole is an object so massive that even light cannot escape its pull. During this video I'm going to explain about how we can prove that, put the maths behind it, some of the features which we can use to observe black holes, and give you a full understanding of what it means to be a black hole. So let's start off with some mathematics. If we want to escape the Earth, we need our kinetic energy to equal our gravitational potential energy. So we need to overcome the gravitational potential energy. Now, that means if I could do some maths, that half mv squared is going to be equal to gravitational constant times the mass of the Earth times the mass of the object divided by the radius of the Earth. If I rearrange that, it means I can find an escape velocity, the velocity of any object, which needs to be greater than a certain value. And this is all related to both the mass and the radius of planet Earth. Now, if you find the escape velocity at the surface of Mercury, which has a mass of 3.31 times 10 to the 23 kilograms and a radius of 2.44 megameters. So take a moment to do that calculation. And I'm hoping you've come up with an answer of 4.25 kilometers per second. So as long as an object is moving up with a speed greater than that, it should be able to escape, in this case, the surface of Mercury. Now let's step this up a little bit here. The Schwarzschild radius is based on this thinking, that what would be the radius of an object that would require the speed of light as the escape velocity. So here we've set the velocity as the speed of light, and what we find out is that there's a certain radius relating to a certain mass, which means even light could not go fast enough to escape such a body. Hence, we've created a mathematical black hole, and we've actually found what's known as the event horizon. The Schwarzschild radius is the point of no return. Once you're within there, you cannot escape, because you'd have to be exceeding the velocity, which is the speed of light, which is not going to happen, as we well know. Now, what's the evidence for these things? Well, there's a couple of things which we think indicate there's a black hole. I say that because clearly we can't directly observe a black hole, because no light is going to escape it, because the escape velocity is greater than the speed of light. But we have some indicators. Our indicators are that gravitational lensing. We can see the bending of light of distant objects, and so this is known as gravitational lensing. We can also see matter falling into the black hole that may rub and get really hot and often emit in the X-ray spectrum. And we can also follow the death spiral of stars as they fall into massive black holes at the center of galaxies. Now, these black holes at the center of galaxies are actually quite interesting because they may come in another guise. That other guise would be as a quasar. Now, quasars are fascinating. My statement from Wikipedia here says that extremely luminous active galactic nucleuses, so these are found at the center of a galaxy, and they're powered by supermassive black holes. And they tend to be of tens of millions of solar masses, and they're often surrounded by an accretion disk. So what's happening here is the gas is falling towards the black hole, and it gets heated up, and it releases lots and lots of energy in that process, in the form of electromagnetic radiation. And this radiation gets emitted, but note it gets emitted along the axis of rotation. So what we've got here is just one clear line, like a spotlight, going out into space. As it happened the first time this was observed, what we see is really, really clear radio waves. And if you imagine then any precipitation, which would mean that spotlight would be shining on the Earth and off the Earth, and on the Earth and off the Earth. And actually, the first observation, there was LGM was noted down next to these first observations, and LGM stood for Little Green Men, because it thought it could be the first bit of alien communication. But actually, we now see that this is another indicator that black holes exist, and this energy is being emitted not from the black hole itself, but from the process, and this is all to do with the conservation of angular momentum. So the density of black hole. Let's think this process and combine some things together. Density is mass divided by volume, and here we've got the volume of a sphere. In this case, if we substitute our equation for the Schwarzschild radius as r, we can then derive the density of a black hole. So as it happens, the density of a black hole is 3c speed of light to the 6 divided by 4 pi 8g to the 3 m squared. Now this is in theory, the density should increase to infinity as you approach the center of the black hole. Final thought here. Imagine you're a god. These are the questions that come up to you. So you created everything? Yes. Including black holes? Yes. Which will, and indeed they will do. There's nothing escaping it. There'll always be a gravitational attraction to black holes, which means that they will at some point encompass the whole universe. Maybe. We will see what other thinking comes about from this, but that's my last thought. So thank you very much for watching this video.